Assalamu alaikum. Bismillahirrahmanirrahim. Rabbi shrah li sadri. This is the first lecture out of the online course series for Geotechnical Engineering 1, and the course code is CE221. In our today's topic, we will be mainly talking about consolidation settlement. Before we go to the consolidation settlement, we'll first have a little look at load. We know that whenever load is being applied on any body, so stresses and strains are produced in that particular body. In elastic materials such as steels or rubber, stresses and strains are produced without any time lag. Whereas in inelastic material, stresses and strain relationships is time dependent. That means when load is applied, signs of deformation occur in a little later while. These are also called as viscoelastic materials, and soil is one good example of a viscoelastic material. So, and also when soils are loaded, they always get some permanent deformation in them. Now we talk about the compressibility of the soil. Now we know that whenever soil, as we have already seen, that when soil is loaded, it will have deformation. So that means it will have some memory that will indicate that it has bore some amount of load in its past. So now we talk about the compressibility of the soil, and by definition, compressibility means it's a decrease in volume that occurs under a compressive forces. Now, what can be the causes of the soil compression? First one can be the compression of the soil particles. Second one is the compression of air and water that is present inside the voids, and the third one is the expulsion of air and water from the voids. So we already know that soil is a three-phase system, as we discussed in our class, and we have a picture here. So if I draw a little picture of a three-phase diagram, so this is in general how soil particles are inside. See here. So these round things are the soil particles, and the spaces in between, like this one, these are the voids, and these are the solid particles. So if it's a unsaturated soil, then these void spaces would be filled with water as well as air, whereas in case of a fully saturated soil, there will not be air would be removed, and the voids will only contain water in them. So coming back to the causes, first one is compression of soil particles. So that means these soil particles, they get compressed or they deform. If that happens, then this is very small in its amount if this compression happens. The second compression or the reason of compressibility of the soil can be compression of air and water in the voids. That means the air or the water that was present inside the voids, it gets compressed. So we now know that air is highly compressible. So that means if air is present in the inside the voids, then it can be compressed to a very bigger amount. But in our Geotech 1 courses, we only deal with saturated soils, and in saturated soils we've already seen that there is no air, and we only have solid particles, and we only have the water inside the voids. And when we talk about water compressibility, we know that water is highly incompressible. Third reason can be expulsion of air and water from the voids, and we are, as we've already seen, that we do not consider air because we are considering fully saturated soils or fully saturated soil mechanics for our course. So that means it is the expulsion of water. So now we have repeating the causes. We have all seen that compression of soil particles is very small, so we can neglect that. Compression of air, and there's no air because it's a fully saturated soil. So, and water is incompressible, so this cannot be a bigger reason for our case. And the expulsion of air, which is not present there, expulsion of water, so this can be a good reason for the compressibility of a fully saturated soil. So we already seen compression of water is very small. So, and we have seen that air is highly incompressible, but nowhere in saturated soils. So in fully saturated soil, compression occurs mainly due to the expulsion of the water. Now we talk about the compression of cohesionless soil. So it compresses in relatively shorter time, or immediate compression is there, and generally vibrations are a quicker method for compression of cohesionless soils, and most settlement occurs during the construction phase of the structure. So we can say that there is no long-term problem of compression in case of cohesionless soil. Compression of cohesive soils. So a saturated soil permeability, soil will compress very slowly. So that means the soil, if it's saturated and it has a lower permeability, so the soil will compress very slowly. And what is permeability? Permeability is indicated by K, and it is generally having the unit of centimeter per second, and we can say that it is the what we can say is the ability of soil to let water pass through it. Though it's a very crude definition, but we will discuss in detail. Our next topic of consolidation is permeability, so we can discuss in detail there, but for now we can understand that permeability is the ability of the soil sample to let water pass through it. If it has have very high permeability, so that means water will quickly flow through that soil material, and if it is a very low permeability, so it will take maybe weeks or months for water to pass through that soil material. Consolidation, that is our main topic for our today's lecture. So compression of saturated soil under static pressure is called as consolidation, or in a simpler term we can say that rate of volume decrease with time. Now it is entirely due to the expulsion of water from the voids, as we've already seen in the causes of compressibility of the soil. So if we consider the example of a sponge, I don't know why I have written freezing here, but it's just like if we have a saturated sponge that is filled with water, and if I try to compress that, we will see that all the water will move out. So if I draw a small sponge here, there's a lot of pores and it contains a lot of water in it. So if I compress it between my hands, what will happen? It will compress almost like this, and what will happen? All the water that was inside the sponge, it will move out. So similarly, the example of the soil permeability or soil consolidation, that our soil specimen is there, and this, if we consider this sponge as a soil specimen, so this has water as well as it has soil particles, and if we apply compressive forces on top, just like by squeezing in a hand, squeezing with a hand, so what will happen? All the water will move out. But now the difference is that in the sponge, water moves immediately outside because it has very high permeability, okay, because it will easily let water to pass through it. Whereas in case of soils, it will depend on the type of soil that we're considering. If it is a low permeability soil, so we are compressing, but the rate of water moving out would be very, very slow, maybe months or years maybe. So water, what happens in consolidation is that water escapes depending on the permeability. So then what will happen? Solid particles will rearrange themselves by rolling, sliding, and then to achieve a tighter packing. So that means that once we are compressing the soil, water is moving out, so there is also a reduction in the volume of the soil specimen. So soil volume change may occur due to bending, distortion, and fracture of the solid particles. So main reason is the water moving out and soil rearrangement. All right, we have already seen that, the rearrangement. So but also there can be a small amount of volume change due to the distortion, fraction, or bending of the soil particles itself. Settlement. So what is settlement? It is the vertical downward movement of a structure due to the volume changes of the soil, or in other words, gradual sinking of structure due to the compression of the soil below. If I talk about settlement, so ST, if it indicates the total settlement, then it is equal to SE plus SC plus SS, where SC is called as immediate elastic settlement, SC is primary consolidation settlement, and SS is secondary consolidation settlement. So I have drawn a graph here. So on the left y-axis, on the left side, we have deformation. Okay, it is increasing from top to bottom, and time is on a log scale from left to right. So this is how a soil particle would compress or settle. The small amount is immediate settlement. Okay, this portion here, this is immediate settlement, and at the end we have a smaller portion of the secondary settlement. So you see here, this huge area, this all is due to consolidation or primary consolidation settlement. So if I take a soil sample, okay, and if I compress it, so initially due to the water moving out, okay, so initially there would be little settlement, that is SE, okay, and then if I further compress it with time, you see here, with the load is there and time is increasing, what's going to happen is that there would be more compression, and let's say the soil reaches this part, and this is SC, that is the primary consolidation settlement. And even if we continue loading our specimen after reaching this SC settlement, there will be further reduction, and then reduction is called as SS, or the secondary consolidation specimen. So just to repeat again, so whenever we are compressing a soil specimen, initially, as you've already seen in the definition, that elastic settlement would happen as soon as the construction work is happening, so it will finish during the construction time. And with later stage, when the structure is there and load is coming on the soil, water will move out due to the consolidation settlement, on there will be reduction in volume, and then soil will be compressing in SC, and after finishing off the primary consolidation settlement, there can be a further decrease in the volume of the soil, and that is regarded as the SS, or the secondary consolidation settlement. So just to go through the immediate settlement definition again, so it is caused by the elastic deformation of the drier soil, and when it happens in moist or saturated soil, there is no change in the moisture content. Primary consolidation settlement, that is the major chunk. We have already seen that the major part of consolidation is this secondary consolidation, all right. So sorry, is the primary consolidation. So that is the result of the volume change in a saturated cohesive soil due to expulsion of water from voids of the soil. Lastly, we have secondary consolidation settlement, or that's also called as creep. So it is generally observed in saturated cohesive soils due to plastic deformation of the soil fabric, and it has been attributed towards with a small colloidal chemical process, but the process is still in theoretical phase. There is no detailed understanding what's actually happening that is causing the creep of the soil. So out of these three, primary, immediate, and secondary consolidation, primary consolidation settlement is much larger and it's easier to predict and occurs at a much faster rate. This is generally what we think, but if we have organic soil, then we also have to pay special attention to the secondary consolidation, because in case of organic soils, the part of the secondary consolidation would be much larger than the primary and the immediate settlement. And generally secondary consolidation starts after completion of the primary consolidation. Now we look at the differences between compaction and consolidation. We have already discussed compaction in our previous lectures, so it will be easier to have a comparison between the two. So compaction occurs by reduction in the in both of them we have reduction in the volume, or we have increase in density. So actually it should be reduction in volume, not reduction in density, right? So the reduction in volume in case of compaction is brought about by removal of the air, whereas in consolidation, reduction is brought about by the removal of water. Uh, Compaction is accomplished by rolling, tamping, and vibration, whereas consolidation is caused by a static load or a structure that we have built. Compaction is quick and it is independent of time. There is no rule of time, whereas consolidation is a time-taking process and it is obviously time dependent. If we go back to the graph that we've already seen, you see here the time is increasing from here to left to right. So with the increase of time, the settlement is also increasing. So that's why it is written here that compaction is a time independent process, whereas consolidation is a time dependent process, and obviously it's very slow process. Compaction is applicable for both coarse and fine grained soils, whereas consolidation occurs generally in fine grained saturated soils. And in case of compaction, we require compactive effort, and whereas consolidation is a drainage process. Now we discuss Terzaghis one-dimensional consolidation theory, or it is also called as a spring model or a spring cylinder model. So to explain this, we will have a highlight or have a look at this one picture here. You see here that we have a box or a cylinder, and then in the cylinder there is a spring, and then there is a valve that will allow the water to move out. So the analogy between the spring cylinder model and the soil is that the spring represents the soil skeleton, whereas the water inside the cylinder represents the pore water that is present inside the voids of a saturated soil. And the valve it represents the permeability. We've already discussed that permeability is the ability of the soil to allow water to pass through it. The same thing is done by the valve. It will allow water to pass through it or not. So what we will do first, if we have this, you see here the gauge, you see here this is the pressure gauge, and this is telling us the pressure of this water that is present inside the container, or in other words it's telling us the pore water pressure. So initially when we apply a load P and we do not allow the valve to let water pass through it, that means the permeability of the soil is 0. What will happen? All the load P that we have applied here, it will be carried by the water, and how water carries by increasing its pore pressure value. So this means there would be increase in the reading of the pressure gauge that is attached to the cylinder, and that would be exactly equal to the load that we've applied. So if we allow the valve to open, what will happen? The water would start gushing out from the valve, alright, and then the spring would start to compress with time. So as the spring is compressing, so load, that means spring is taking load. So at a certain time, the load of P that is implied on the system, some of it is taken by the spring and some is taken by the water. And after a certain while, this condition will happen that all the excess water has moved out, alright, and there would be no more water coming out of the valve. So at this time, all the load is taken by the spring and there is no load on the pore pressure or the water inside the cylinder. So at initially when there is no load, pore pressure is 0, that is indicated by this drawing here, and once we apply a load here, so that is equal to P over A. P is the applied load and A is the area of the cross section of the cylinder. So after a certain while, when we allow some valve to open, so pore pressure would reduce from the maximum value, that was P over A, and at the end when all the excess water is moved out, pore pressure would again become 0. That was also the initial condition, and all the load P would be carried by the spring itself. So if we see here, Total pressure of the system is equal to PS plus PW, where PS is the load carried by the spring and PW is the load carried by the water. So if I go back to the diagram here, initially in this case, there's no load, so there's no pressure. And once we applied this external load P, so at the time when the valve is closed, the pressure on the spring is 0 and pressure of water is equal to the P, that is the applied load. And once the valve is open, and at this time PS, that is the spring pressure, would be greater than 0 and water pressure would be less than the applied pressure P. And at the end, once all the excess pressure has been dissipated, so at this time pressure of the spring would be equal to the total applied pressure and the pressure in water is equal to 0. So now if we consider a actual field condition where there is a clay indicated by these blue dots and gray background, so this is a saturated clay specimen and it is bounded by sand on top and the bottom. All right, so if we apply a differential stress of delta sigma on top of it and we assume that same amount of stress is reaching at the clay center, the height of the clay is h. So these graphs will help us understand the condition of the soil due to the application of the delta sigma stress with time. So at an initial time of t is equal to 0, before we talk about it, there is little explanation here that total stress in a system, that is indicated by this sigma here, it is equal to the effective stress, that is sigma dash, plus delta u, that is the change in pore water pressure. Now delta sigma is the, we can say that it is the effective stress or load carried by soil grain. Or if we consider the example of the spring model, then it is the load carried by the spring. So the total stress that we applied, some of it would be taken by the spring or the soil structure and some of it would be taken by the pore water pressure. So coming back to the diagram here, so at a time t is equal to 0, there is total increase, the total stress increase is equal to the delta sigma, that is the load applied, this the one mentioned here, and pore water pressure increase is equal to the delta sigma or the total stress increase, and effective stress is 0 because there is no water moving out and all the load is initially carried by the water. And after a certain while, that is between 0 and a time infinity, total stress is again indicated by delta sigma. Pore water pressure would be somewhere lesser than the delta sigma. All right, this is delta sigma and this is what the pore water pressure value is, and delta sigma would be also lesser than the total value. And at the time infinity, when all the excess has been dissipated, total stress remains the same, delta sigma. Pore pressure now becomes 0 and delta sigma is equal to the total effective stress. So I would suggest you guys that you go through the lecture again and with the notebook in your hands, write down your queries and we can discuss that in our interactive sessions during our class time. All right, take care. Assalamu alaikum.